Okay, today's lesson 2.1, it's our first lesson in Unit 2. We're going to be looking at the greatest common factor and finding the greatest common factor between two or three numbers and monomials. So that'll be a new term for you probably. The first thing we want to do is kind of review our divisibility rules. What we talk about when we mean divisibility rules are testing numbers for divisibility. So if it's divisible by 2, what we look at is that it's an even number. Okay, so the rule is that we have an even number. All even numbers end in 0, a 2, a 4, a 6, or an 8. So you should be able to identify what numbers are even. If it's even, it's divisible by 2. Therefore, it's not a prime number. Okay, so that's one thing when we start looking at divisibility, we have to kind of identify the two different types of number types. We have prime numbers, right? Prime numbers have exactly two factors. One and themselves. Okay, 2 is the only even prime number because 2 satisfies that definition. It has exactly two factors. You can make 2 by taking 2 times 1 and nothing else. The other way we classify numbers are composite. Composite numbers can be broken up into their factors. Composite number, if you think about the root word of that, composed of more than just 2 factors. So testing for divisibility helps. All composite numbers that are even are divisible by 2. If it's divisible by 3, add the digits of the number. Okay, and they will equal a multiple of 3. So the sum of the digits is divisible by 3. I like that way of wording it better. I'm going to erase this and start over. The sum, that's okay, sum of the digits of the number is divisible by 3. So what do you mean? Like the number 423, right? The sum of the digits would be taking 4 plus 2 plus 3. 4 plus 2 plus 3 equal 9. 9 is divisible by 3. Therefore, 423 is also divisible by 3. For testing for the number 4, the rule that you would test for is to look at the last 2 digits are the number, whatever makes up the last 2 digits, are divisible by 4. So the number 128. So notice that this is going to help us with numbers that are greater than 100, like larger numbers. If we look at the last 2 digits are 28. 28 is divisible by 4. Therefore, 128 is also divisible by 4. Divisible by 5. The last digit is 5 or 0. If it's divisible by 6, the number is divisible by both 2 and 3. So you first look at the number. You see if it's even. If it's even, it's divisible by 2. You add up its digits. If it's divisible by 3, then it can also be divisible by 6 because it has a factor of 2 and 3, and if you combine 2 and 3 through multiplication, you get 6. 9 is similar to 3. So the sum of the digits in this case are divisible by 9. So back up to our example from number 3. This 423 is also divisible by 9 because when we added the digits, it was divisible by 9. Okay, so it could be any multiple of 9 to make it divisible by 9. And 10 is the easiest. Last digit is 0. Okay, why was it important for us to go over these divisibility rules? Because when we start to find the common factors, we're kind of factoring out all the common factors of 2 numbers that we're comparing, or 3 numbers that we're comparing, and so it would be nice and quick and easy for us to be able to test some of these smaller numbers to see if they're divisible by that. Okay, so we're going to find the greatest common factor of 45 and 60. And to do this, I'm going to show you a method. It has multiple different names. Don't even know who invented the method. But there are several ways to find a common factor. You can list all the factors of the 2 numbers, but when the numbers get large, we tend to then miss some of the building blocks and some of the pieces that put it together. But if we use the divisibility rules, we could take 45 and 60 side by side and kind of divide them by common factors using those divisibility rules. So I look first maybe at 2. Are they both even? And the answer is no. Then 3. I could add up 4 and 5 and get 9, and 6 and 0 and get 6, and both 9 and 6 are divisible by 3, so I know that 3 is a common factor. So I could start there, or I could look for another common factor. Sometimes taking a bigger common factor has less steps. So one of them ends in 5, one ends in 0, and that's the divisibility rule for 5. So I could divide by 5. So 45 divided by 5, and I put that answer down here. 60 divided by 5 is going to be 12. Now let's look at and see if there's any common factors between 9 and 12. And I definitely know of 3 because 9 is divisible by 3, and if I add 1 and 2 together, I get 3, which is divisible by 3. So I bring another little rung of my ladder, or a tier of my cake, depending on what you want to look at. And I take 3 into 9 and 3 into 12, and I look for common factors. When I see no common factors, I'm done. My greatest common factor could be found by multiplying these numbers together out here on the side. So GCF for 45 and 60 are equal to 5 times 3, which is 15. Let's try these 2. Same method. We want to go ahead and put them side by side. And then I'm going to start doing some divisibility rules. And I look at 88, it's even, but 63 is not. I add up 8 plus 8, and I get 16, not divisible by 3. 88 is divisible by 4, right? But 63 is not. I try 5, doesn't work. I try 6, they had to be 2 and 3, and since we already ruled those out, that's not even a possibility. I could try 7 because that wasn't a rule, so sometimes you have to test for 7, even though we don't have like a little rule that we have to do. Because 63 is divisible by 7, but 88 is not. Then I try 9, doesn't work. The only common factor that these 2 have in common is 1. So in this case, the GCF is equal to 1. And these 2 numbers are called relatively prime. And I want you to write this down. Okay? Relatively prime, because 88 is not a prime number, right? It's even, it's not prime. 63 is not a prime number, it's a composite. It's composed of lots of factors. But together they are relatively prime in the way that they relate to each other because their GCF is equal to 1. So if you're ever asked, tell if these numbers are relatively prime, basically we're wanting to know, do they have any common factors other than 1? If the answer is yes, then find that common factor. But if not, then say yes, they are relatively prime. All right, When do we use this stuff? Why do we need to know about the greatest common factor, and how does it help us in the real world? Well, if you had a situation like this, little Alicia and David are putting together snack packs for a large group of hikers. They had collected donations, and when they counted their donations, they had 160 apples, 320 carrot sticks, and 400 celery sticks. And they needed each snack pack to be the same, right? And no leftovers. So what's the greatest number of snack packs that they can make, and what is in each snack pack? So in this case, we're going to take and find the greatest common factor of the apples, the carrots, and the celery sticks. So if we find the greatest common factor of all of these, again, some large numbers here. We know that they all end in 0, and we can start with 10. Let's do that and break them up a little bit smaller. So we'll get 16, 32, and 40. So 16, 32, and 40 are all even. I know they are all divisible by 2, which means that there might be even something else they're all divisible by. So I look for like the largest thing that I can find that they're divisible by. So let's try 8. Again, using larger factors on the outside are less rungs and steps on the inside. So 16 divided by 8 is 2, 32 divided by 8 is 4, and 40 divided by 8 is 5. So what I want to know is, do we have any common factors between 2, 4, and 5? 2 and 4 are even, but that 5 kind of throws things off. Since we're down to the row that has no common factors for all 3 numbers, we're done. And our GCF is found by multiplying these 2 numbers. So the greatest common factor is going to be 10 times 8, which is 80. We will make 80 packs. And each pack will have 2 apples, because 80 times 2 is 160, 4 carrot sticks, and 5 celery sticks. And they will all be the same. Okay, this next part, what are monomials? And we're going to be factoring monomials and finding the GCF. So the first thing we're going to do is define it. It's a kind of a crazy term. By definition, a monomial is a number, a variable, or the product of any one or more variables. Last year you might have started to learn a little bit about combining like terms. Those terms you identified were monomial terms. Okay? So here's some examples of what a monomial would look like. There's a number, right? It's a number. It could be any number. That's a monomial. A variable could be any variable. X, A, Z, whatever the variable is. A product of a number and one or more variables could look like 7x or 25mn squared or 24x or y cubed z squared. Those are all monomials because their relationship between the numbers and the variables are all multiplication. These are not monomials. The first one is 7 plus x. That's 2 monomials joined together by addition. They call that a binomial. There's 2 monomials. Mono meaning 1, bi meaning 2. 25m minus n squared. So again, we have that subtraction thrown in there. That does not fit the definition because in the definition, it clearly says the relationship can only be that it's a product of the number and variables, not addition, subtraction of number and variables. So number 2 is also a binomial. And then the third one, 24 plus y cubed plus z squared, trinomial. We call that a trinomial. Once you get past 3 terms or 3 monomials put together, it becomes a polynomial. And in 8th grade, you're going to be factoring and doing all kinds of fun stuff with polynomials. So let's factor a monomial. So we're going to factor the monomial 12x squared y. And the first thing, obviously the answers are already up there. The first thing that's going to happen is you're going to factor the number 12. When we factor the number 12, what does that mean? We want to break it up. Oops, I'll go back. We want to break it up. So how would you factor 12? I would look at this right here, and I would take the 12, and you could do a factor tree. And you could say 12 is made up of 3 times 4, and 4 is made up of 2 times 2, so that the prime factors of 12 are right here. Okay? So that's 12 broken up into its tiniest, smallest parts. If you like that ladder method that we were using before, you could still do that instead of a factor tree. I always start with the smallest prime number, which is 2, and I divide, again divisible by 2, and then the numbers outside are my prime factor pieces that make up 12. Then I have my variable part of that monomial. So x squared times y, except for x squared has an exponent. So we basically want to take away the exponents and write the repeated factors. So we want to take this x squared and break it up into x times x to show all the parts. So notice that in your factored, your final factored form, this monomial has no exponents and no composite numbers. Okay? And it's all associated through multiplication. If you took 2 times 2 times 3, you would get 12. X times x is obviously x squared times y. It's the same thing, but broken up into its pieces. So let's try a couple. Factor these monomials. So break them up in their tiniest little parts. So looking at the first one, the number 5 is prime. So this breaks up into its smallest parts by just splitting them up and saying 5 times x times y. That is the factored monomial. However, 28 is a composite number. So I would have to do a factor tree or the upside down division, which I prefer because I think it's a little more compact. And I get 2 times 2 times 7. So 2 times 2 times 7. And then I have 2 factors of A and 4 factors of B. And there's my final solution. All right. So let's try to factor, find the greatest common factor of these two monomials. So one thing we can do is we can put them side by side. Just like we did before. The number part will work the same. Okay? So we look and try to find, so we know we can divide both by 4. So when we take this and we divide it by 4, we will be left with x cubed y squared. 20 divided by 4 leaves us with a 5x y cubed z. Now we compare, and the coefficient here is 1, right? So we have no more numbers to work with, we're down to letters. But this first one has an x, and this one has an x. So I can divide by x. If I take x cubed divided by x, let's think about what that looks like. X times x times x divide by 1x. I can cancel off one complete x, and I'm left with x squared. So what have I done? I've taken this, which is like an exponent of 1, and I've subtracted it to leave me with 2. Bring down the 5. This is like 1, and if I divide it by 1, it's completely gone, right? X divided by x is a factor equal to 1, and they both cancel out. So I'm left with y cubed z. Now my common factors are y. So I have 2 y's here and 3 y's here. What's the most that I can divide by? The 2, right? If I divide by y squared, I would be left with x squared. And then over here is, and again, this is why we use dot multiplication, because once we are left with variables, our GCF is 4xy squared. This is a factor of both of our original monomials. let's try these out then. If we're going to factor them, one of two ways. We have, looking at just the numbers, we could take 36 and 45, find a common factor. 9 times 4 goes into 36, and 9 times 5. There are no common factors between 4 and 5, so for this one, the GCF would be 9. And now let's look at the variables. They both have a factor of x. The first one has 2 factors, the second one has 4 factors. The most we can use are the ones with 2. So the GCF becomes 9x squared. Let's try this one. 5, 25, and 50. If we're dividing, we could divide everything by 5. And since 1 is not a common factor of, well, it is 5 and 10, but they don't have any other common factors besides 1, our GCF would be equal to 5. Notice this has an A. There are 0 A's and only 1 A here. The first monomial has 0 B's, 1B and 1B. Therefore, there are no variables in common that we can include for our answer. Okay, the last thing we're going to do is watch a short video on finding the GCF of monomials.
Find the greatest common factor of these monomials. Now, the greatest common factor of anything is the largest factor that's divisible into both, if we're talking about just pure numbers, into both numbers, or in this case, into both monomials. Now, we have to be a little bit careful when we talk about greatest in the context of algebraic expressions like this, because it's greatest from the point of view that it includes the most factors of each of these monomials. It's not necessarily the greatest possible number, because maybe some of these variables could take on negative values. Maybe they're taking on values less than 1, so if you square it, it's actually going to become a smaller number. But I think, without getting too much into the weeds there, I think if we just kind of run through the process of it, you'll understand it a little bit better. So to find the greatest common factor, let's just essentially break down each of these numbers into what we could call their prime factorization, but it's kind of a combination of the prime factorization of the numeric parts of the number, plus essentially the factorization of the variable parts. So if we wanted to write 10, we could say, or if we were to write 10cd squared, we can rewrite that as the product of the prime factors of 10. The prime factorization of 10 is just 2 times 5. Those are both prime numbers. So 10 can be broken down as 2 times 5. C can only be broken down by C. We don't know anything else that C can be broken into. So C, so 2 times 5 times C. But then the D squared can be rewritten as D times D. D times D. This is what I mean by writing this monomial essentially as the product of its constituents. For the numeric part of it, it's the constituents of the prime factors, and for the rest of it, we're just kind of expanding out the exponents. Now let's do that for 25c to the third d squared. So 25 right here, that's 5 times 5, so this is equal to 5 times 5, and then c to the third, that's times c times c times c, and then d squared times d squared is times d times d. So what's their greatest common factor in this context? Well, they both have at least 1 5. They both have at least 1 5. Then they both have at least 1 c over here, so let's just take up one of the c's right over there. And then they both have 2 d's. They both have 2 d's. So the greatest common factor in this context, the greatest common factor of these two monomials, is going to be the factors that they have in common. So it's going to be equal to this 5 times, we only have 1 c in common, times, and we have 2 d's in common, times d times d. So this is equal to 5c d squared. And so 5d squared, we can kind of view it as the greatest, but I'll put that in quotes where, depending on whether c is negative or positive and d is greater than or less than 0. But this is the greatest common factor of these two monomials. It's divisible into both of them, and it uses the most factors possible.